former website, it was still working. Unfortunately, now it no longer works. But you've probably seen or heard about this GPT-3 model that is quite impressive in some respects for generating content and knowing a lot of concepts. You've seen probably this website. If you haven't, this one still works. If you click it, every time you reload your browser, it will generate a new picture of a person. And if you do that a couple of times, you can train yourself in seeing and learning to recognize whether or not they're fake. They're really good, but if you look closely, you'll see that perhaps the earring on the left is different from the right, and some kind of small things that will tell you that they're fake. And then, of course, machine learning is being used for speech synthesis, all kinds of other things that you've probably seen before. So with this slide, I just wanted to set a bit of context that machine learning is popping up in many places that are becoming practically relevant in daily lives, in our daily lives too. And just a bit of a background, I'm assuming that most of you have seen some of this before. If not, remember the question for the end. I typically think of machine learning here in this context as just a different way of solving problems. So think of this typical example of machine learning 101. So the machine learning approach here, I'm getting a message that my internet connection is unstable. If anything happens, let me know. I can try to turn off my video. The machine learning approach to recognizing cats is very simple. You take many images of cats and perhaps not cats, in this case dogs, and you label them. You tell them this picture is a cat, it's true. This picture has a label true, it's a cat. And these two are false because they are not cats. We could also decide to label them with cat and the word dog, but for now, let's just do binary labels, true and false. And the idea then is that you learn by example. You look at many pictures of cats, and at some point, hopefully, you'll build some of an intuition or an understanding of what a cat is and what a dog is in this case. If you have enough of those pictures, hopefully you'll be able to recognize and identify other cats. That's typically done in machine learning using so-called neural networks. And all they do, will be examples later, is take as input that picture and map that picture, that input, to an answer. In this case, a label, maybe true or false. And the traditional approach, I know this is a bit cheating, but I called it the human approach here, would be, for example, writing an algorithm to solve the problem of identifying cats. And that gets out of hand really quickly because you want to have a function that says if a picture is a cat, true or false. There's so many things you need to worry about: the orientation of the picture, the lighting of the picture. If it, if it has whiskers and it has manes, it could still be a lion or some other predator. So you'll hopefully realize that approach is difficult for this problem. So let's move on to some of those types of machine learning that I want to consider. And I'm seeing that my slides are lacking on the stream. Let's give it a second. Can you confirm that you're still seeing the cats and dogs picture?
Yeah.
Interesting. Give me one. If this doesn't update because I'm streaming it from my iPad that used to work, then I'll just do it from my Keynote on my computer. Just trying very quickly. Better?
Yeah, okay.
Did that? Okay. Let's continue from here. If it happens again, we'll go to Keynote. Okay, so I wanted to distinguish very quickly, since this is also the first talk in the session, 3 types of machine learning, so that we can set the context. So what we just saw is this supervised learning, in which I take essentially many examples of input X and answers Y. In this, they were true and false before. And what I'm trying to do mathematically, in a sense, is learn this distribution, learn this conditional probability of, given the picture X, what is the probability for label Y, right? That's a classification problem. There are other types of machine learning that are typically distinguished. For example, unsupervised learning, where I would do the following. I would just have the data set only, no examples, and I would try to just learn the distribution of these pictures. And if I do that in a clever way with the generative model, then maybe I can even draw samples from this distribution. And if I learned the distribution correctly, those would be samples of pictures of cats in this case. And then there's another type that I want to mention, because we're moving towards a bit of an AI setting here, which is reinforcement learning. And this deals with learning a so-called policy, which is more, think of that as a strategy. It means if I'm in a given situation, what is the best move, the best action that I can take in order to achieve some goal. And this could be, you know, multiple steps. It could be playing a game, for example. I'm speeding up a little bit to make up for some time. Right, so these 3 types of machine learning are typically distinguished, and each of them also has a particular use in physics. And then the examples I'm giving here are not the only ones, but these were the ones that came to mind for me. So supervised learning can be used, for example, in the problem of finding phase transitions or identifying phases. The other methods can do that too, but let's dive into this one first. So the whole problem here is the following. Imagine that in an experiment or in a numerical simulation, you have some parameters, maybe temperature and some other pressure or some other variable. And in that experiment, you can, you know, set the temperature and draw samples. Each of those dots would maybe be a measurement of, I don't know, some quantity, density, or some other susceptibility that you are measuring at each of those points. And imagine that I have a very fine grid of those points, ideally, of course. Then the sole question that I wanted to ask here is, if there are 2 phases in this problem, phase A, everywhere around, and this white area would be some phase that I called phase A, and inside this blue ellipse is phase B. Can we then find this phase transition boundary from all those measurements, right? So without turning on our physics brain and trying to interpret what would change there, just from those measurements of susceptibilities or something else, can we find that transition? And the answer is yes, and it can be done in a couple of different ways. And I'm sure that today, I've seen in the talks and the posters, there are other methods to do this that I'm going to describe here. So stay tuned for those. One way of doing that identification would be as follows. Let's go to a one-dimensional axis for now. So I only have temperature here. And you all know this model, just a spin model, for example, the Ising model. So now I can divide this temperature axis into 2 extremities, one on the very right-hand side where the temperature is very large, and one on the other side, on the left side, where the temperature is very small. And more often than not in physics, you have such regimes in which you know the behavior of your system, right? So in this case, if I have a system of spins that I didn't explain, but I hope you know about, these images, each pixel is a spin, white, for example, pointing up and black pointing down. And at very low temperatures, we know from the spin model that they try to form clusters. They all start to align, right? I'll get back to what's up here next. And on the other hand, in the other regime, in very high temperatures, the system is completely disordered. The spins start to randomly point up and down, and there's not much of an alignment between the spins. And so in those 2 regimes, the high temperature and the low temperature, I know what the answers are. Namely, I want to know the probability given such a picture. I show you one of these pictures and I ask, what do you think the probability for it being below some critical temperature is? And the critical temperature, I'm assuming, exists. It may not, but it's somewhere in the middle. And the probability that the temperature is above critical. Well, for these pictures, I know I made those pictures. I know that I generated them at low temperature. So I know that for these pictures, these are the correct answers. They're 100% certain that these pictures come from T below TC and 0% from above. And of course, on the other end, it's the opposite. Now, the funny thing you're seeing here is a depiction of a neural network. And without going into detail about what they do, that's just the mechanism. It's a map that each of those yellow dots would take as input one of the pixels here. So for the actual neural network here, if this is 40 by 40 pixels, there would be 40 times 40 of these yellow inputs, many lines that are representing weights. I'm sure you've seen all of those, but whatever it does, it takes the picture as input right here, and then out comes a probability that for which it thinks it is below TC or above TC. And if we have that network, right, once we train it, once we update all those green and well, actually the black lines to reflect these probabilities, then now I can do something else. I can go to my experiment or my numerics, and I can start generating pictures at temperatures that are not in those extreme regimes, for which I don't know for sure what the answer is, and then feed those pictures into my neural network too, and see what it says. And for this one, for example, it said, well, it looks very similar to the low temperature ones, T below TC. I'm 80% sure it's that, but perhaps with 20%, it could also be from a high temperature regime. I can do the same at the other end. In this case, because I chose the data this way, it's symmetric because I know the answer here. But you can keep doing that for all the pictures in between. For example, something like this, and then make a plot of the probability with which you assign T larger than TC for that sample. And you will find, hopefully or ideally, such a curve. It depends a bit on some settings that are technical details. And let's say there's some, this goes from 0 to 1, the labels are missing here, and there's 0.5 in the middle, 50%. Then I would argue that at 50%, if I'm 50% sure it's below TC or 50% above TC, I apparently cannot decide. This is where I'll put the critical point. So this is where I would then say, here we find the critical temperature. Now, all of this relied on knowing these extreme regimes, right? It relied on me knowing what the answers were there, and that, typically you can do in physics problems, but we can also insist otherwise and say, I don't want to assume anything about my model because I maybe don't know what the Hamiltonian is, or I have a hunch that what I think it is not actually correct. So maybe we can try to do something else. And that's where learning by confusion came into existence. It turns out that physics data is actually much more structured, not surprisingly perhaps, than pictures of cats and dogs. And one of the reasons is that we have that axis that I just drew before. We have such an axis that maybe temperature or some other parameter that we can order our data by. And ordering cats and dogs along some parameter that you can tune is not very intuitive, it's not very natural. But in physics data, because we have a Hamiltonian and we have a parameter, it is. So let's see how that would work, purely from the fact that we have such an ordering, okay? So imagine that this is my axis, my temperature axis, and these dots are measurements that I took. And of course, by eye, for us now, we can clearly see that there is a transition from blue to orange here, okay? But for the sake of understanding, let's imagine that we cannot see what these colors are or whether there is a circle around them or not. These are just some representation of lots of complex numbers. But let's assume that I pick the transition to be here. I just guess, okay? So I guess the transition point along that t-axis that I just drew, and everything to the left of that I call phase 0, label 0, and everything to the right I call label 1. That's a choice I made. And then I say, okay, well, if this is a correct labeling, then what I would interpret from this labeling is that, sorry, that's too much at once, is that up here, is that, well, all of the blue ones have label 0, so blue must be label 0. And the majority of these orange ones has label 0, so I would conclude that orange has label 0. But if that's true, then these last three, they just must be incorrectly labeled. Right? I just made a mistake. They are not labeled correctly. And if we count them, I think there's 28 or so of these dots. Not so important, but let's say 28. Then 3 out of 28 are incorrect here. Well, otherwise, the performance, I would say, would be at some value. Let's say that would be 25 out of 28 are correct, right? If this is just on a 0 to 1 scale, right? So that's if the transition is here, okay? I can move that transition point around. I can do something silly and move it all the way at the very end, meaning I say there's no transition in this data. And then every, the blue is still label 0, orange is label 0, but perhaps a bit surprisingly, it's fully consistent. It is indeed correct if these are the labels, that the labeling that I made is fully consistent. So I get 100%, like 100% correct, where 28 out of 28 are correct, right? And I can keep playing this game. In particular, there is another important point where I get this 100% correct, which is if I put the transition in the center, because now blue has label 0, orange has label 1, and none of the orange ones are labeled incorrectly if I assume these labelings. None of the blue ones are labeled incorrectly, so that's good. And then you can finish this game by yourself. There's one more point that is interesting to look at, which is the worst point you can find. Namely, if I happen to put this, guess this transition point right here in the middle of one of the two phases, because now there are 7, if I count correctly, 7 orange dots with label 0 and 7 with label 1. So I don't know, like it's 50-50. If I pick label 0, then all of these label 1s are incorrect. If I pick label 1, then all of these are incorrect. Doesn't matter which one I pick, it's always 7 out of 28 in total that are incorrect. And that gives me the lowest performance you can find. And if you keep doing this, and it's obviously symmetric to the other side, you will find this particular double, like, or triple peak shape, this W shape we called it, just for the letter. And finding this central peak, if you can do that in your data, if you can just guess labels and see which ones are consistent and what I call performance here, you'll find such a peak structure. Maybe not always as nice as this one, but that depends on the tweaking. And finding that peak will find you that transition point, right? And I could go on forever about this method in more detail, but one thing that you might ask is, with 28 points, that's fine, but if I have 10,000 points, then I have to start guessing all of this. That's not very efficient. And you would be correct. There are some naive tricks you could do. Of course, if you happen to find, if you pick a transition here and then 10 data points further ahead, then you find this upward curve, then you can start making larger, you can start making larger jumps towards that peak. It could also be that you find yourself here, you don't know. But that fact that there is this slope in these curves allows you to do something much more efficient. And before I say that, I wanted to mention that in principle, you could do this in 2D too, right? It would just mean you have to take different cuts through your data and repeat finding this W. So you find if in perspective, you should find that W somewhere there, right? And the same is true here. You would find that. But that would require many, many scans and line cuts through your phase diagram. And that's not very efficient either. But all of that can be made more efficient using something from computer vision. And in computer vision, it's called snakes. And if you're interested in that, there's a reference. This can all be made fully autonomous. You have this sort of, imagine that you have a snake like this. It can be tied at two ends, or it can be, it can bite its own tail. But along this snake, you have many nodes, and each of those nodes will move perpendicular to their position, trying to optimize that W. And so it will automatically, like you see in this picture, it will automatically, time flows up here, rotate and wrap and shrink and grow and wrap around a phase. And this can be done in real time for complex data sets. All right, so in view of time, let's move on to the next bit. And for each of the next few, I only have a few things to say. So please feel free to ask me about them afterwards. And I know I should say, I know I already said that there's many other works of supervised learning and unsupervised learning for finding phase transitions. And stay tuned for some other talks that I saw in the session today, because they will show other methods. All right, good. So we had supervised learning, we had unsupervised learning. Remember, this was about trying to learn P of X, given some data set X. And P of X, compare that with the psi of X, for example. These are obviously complex numbers. They are amplitudes, and the P's are probabilities. But if your wave function is real for starters, and there's other things you can do, then if it's real, then we can just take the square root of these psi's and get to probabilities. Or sorry, apps of psi squared would be probabilities. And you could try to learn wave functions. So that's something you can do with unsupervised learning. Learning a distribution for wave functions. And if you haven't, you should look, for example, at this package called netget, which is centered around having representations of wave functions in the form of neural networks. One of them being shown down here. Don't fret about what this type of neural network exactly is. Netget has all of these things built in, and it has extensive tutorials if you want to see how you could, for example, find ground states of your favorite models in the form of a neural network. And why I think this is interesting is for something called quantum state reconstruction, also called tomography. And that idea I wanted to sketch very quickly. So the idea is, let's say we have an experiment with maybe only a few, let's say 4 atoms. They're 2-level, they could be qubits, but in this case, let's think of them as 2-level atoms. So they have state 0 or 1. And every time I do my experiment, I measure and I project it, and I get, so this would be measurement number 1, measurement number 2, and 3, and so on. And I do 10,000 of them. And every time I record if atom number 1 was in state 0 or 1, and atom number 3 was in state 0 or 1, etc. And then the question is, if I have this distribution, this data set, can I try to infer what the underlying wave function was that I'm collapsing every time? Well, if I do that 10,000 times, then perhaps I can make a histogram of that. So I just count how many times do I see all zeros, how many times do I see 1001, for example, and this was normalized. And of course, this histogram depends on the state you're looking at, right? That's the whole point. But if I do that for 4 qubits or 4 atoms, you see I have 16 outcomes. If I do that for 50 atoms, then 2 to the 50 is way too many to make a histogram of, because I would have to do at least to do the 50 measurements to have the opportunity of seeing all of them once, let alone build a histogram. So instead of making that histogram, you can do something else and ask yourself the following question. If I give you, let's say 1,000 samples, I do the measurements 1,000 times instead of millions of times. And then I ask you, given those 1,000 samples, what is the most likely distribution from which they were drawn? Or said otherwise, what is the distribution for which those 1,000 samples are the most likely samples? And that's a question that you can answer, for example, with these RBM neural networks that you update based on the samples that you've seen. And empirically, they seem to be doing very well. I don't know of a full answer for why, for example, these RBMs do so well at approximating wave function distributions, but they seem to do so. And moreover, once you have such an RBM, such a trained neural network wave function, you can sample it. You can ask it, you can draw more measurements from it numerically, and you don't have to do the experiment anymore. This is much more efficient. And if you can do that, then I think the take-home message here, and I think now it's frozen again. Let's see if we can do the same trick. Turn off mirroring and then turn it back on. Here we go. If you can do that, then instead of doing a very complex measurement, for example, something like measuring an entanglement property, which would require duplicating your system and doing all kinds of involved swap operations on them. Maybe your experiment doesn't even have the capabilities of doing that. Then if I can do a bunch of very quick, simple ones, and I can do 10,000 or 1,000 simple ones, train this network, then I can start drawing samples from that and hopefully get to do, then I just have a numerical representation of my wave function. I can do measurements that otherwise would have been very complex to do in real life, or maybe even impossible if my experimental capabilities, I don't have enough lasers or something of the same sort, right? So I think that's an important, direction for trying to analyze and help understand or help work with experimental data, for example. And then by that, hopefully freeing up time for the experimentalist to think about more interesting experiments rather than having to do very tedious measurements to get to some information. All right, so reinforcement learning is the last one I want to talk about. And again, everything froze. This is the last attempt. I'm sorry about this freezing. It's also a first for me. Reinforcement learning, there we go. So reinforcement learning, like I said before, is at least for me, a step in the direction of AI a bit more. Namely, it deals with an agent, let's say represented by a neural network, doesn't really matter. It's something like an AI that can perform actions on an environment, and that could be, think of the environment as a board game or whatever situation it's in. Your robot vacuum cleaner could actually be in an environment which is your apartment. And in every state, the agent, your robot, can take an action, perform that action, and then the environment tells the agent you did good or you didn't do so well. So that would be the reward. And what the agent is doing is you give it a task, namely clean the entire apartment, before tonight, and it will start learning how to do that and maximizing this future expected reward. So it's trying to say, by the end of the day, I want to have the largest reward that I can, and getting the largest reward might not mean doing the best thing immediately, but it might mean waiting for a bit before cleaning this or cleaning that. And so these feedback loops for reinforcement learning are important, and you've probably seen examples of such algorithms, most particularly probably AlphaGo, solving this or reaching grandmaster level in chess easily, solving Go, meaning defeating top Go players. And there's a new version, Mu0, which doesn't even know or get to know the rules of the game. It has to figure out the rules of the game it's playing as it's playing. And these are all, there's more behind the scenes here. There's not too complex, but there's extra components that are not just reinforcement learning in here. But the idea is exactly that. Given the current state of the game, which piece, for example, do I move next in order to finally at the end win the game? And in view of time, I won't have too much detail here, but the thing that I liked working on very much is that in quantum error correction, there's something called a surface code, where each of these, each of the vertices, each of the corners here are qubits. And all of those qubits together, they represent a so-called logical qubit. So this whole picture is a qubit that can be in some superposition of a 0 and a 1 state. And the idea of having so many qubits for just one is that you can make it robust against noise and disorder, topological in this case. It doesn't really matter. The point is these red dots here are so-called defects. They are errors. And you want to remove those errors, and you can do that by, they can move diagonally. And if you move them on top of each other, or if you move them to the boundaries, they disappear. So this now becomes a game, right? It becomes a game of, given this picture, how and where do I move these qubits in, for example, the fewest amounts of moves, or in which order should I move them? Because it could be that the order matters. This is a problem that you can solve with such reinforcement learning techniques. The last thing I wanted to say is that I talked a bit about these three different methods, but you can also start combining them, and that's what people are doing and have been doing. Like an obvious candidate for where these methods could help is, of course, in experiments. Trying to tune and optimize experiments. You know, if you want to have the best conductance to your quantum point contact, the nicest plateaus, the best Coulomb diamonds, etc. These methods could help. You know, sometimes students take 2 weeks just trying to tune and optimize the experiment. And perhaps this can be done in a more clever way. And maybe even more interesting is designing experiments. And also for that, I saw that there's something on our program for experimental design, where in this particular paper, they designed an entire optical table for finding a 3-photon entangled state. So I think these are very interesting things, and probably in this direction is where we'll see a lot of work in the future. All right, so I think my time is up. I wanted to, maybe I can just show this slide, a few ways about when I think machine learning could make sense. Perhaps I'll leave this for you to look at by yourself. And then, as a bit of shameless advertising, I wanted to quickly flash quantum games so that it's on the record. You should check these out if you want to, you know, play a fun game, but also if you want to see if you can teach your 10-year-old niece or nephew about quantum. With that, I think, let me leave this open, and thank you very much for listening.
Okay, thank you so much, Evert. Now time for questions. As I said before, if you have a question, just let us know through the chat, and then I'll invite you to make your question. And then you can unmute your micro and switch off your camera if you will. So I don't know if there are any questions. We have time for a couple of or 3 questions. So
you can go back to any slide if you want. It's a bit of an overview.
maybe to break a little bit the ice, let me make you the following question.
Sure.
Usually, I mean, it's the usual question you probably get when you give a talk on machine learning, right? Usually machine learning or machine learning algorithms, they need big data to operate efficiently, right? And then the usual case is that if you are doing experiment or you are doing some theory in condensed matter physics, you don't have so much data.
Yeah.
And then this is the particular case of phase transitions. So
Yeah.
I was wondering, you talk about here about the supervised learning, but probably there are some other strategy, like some kind of unsupervised learning strategy that allows us, or that allows to get rid of the need of having big data, right, in the problem.
Big data, yeah. So one thing I wanted to mention is that, for example, this learning by confusion requires the same amount of data, but you don't have to have the labels. So it's a sort of semi-supervised, if you wish. But you're right. If you don't have large amounts of data, then I think that was on the slide before. This you won't. For one, you might not have the accuracy you want, or in the worst case, right? If you don't have finely spaced data, you cannot determine your transition very finely, very precisely. But also, perhaps if you have even fewer data, you won't be able to train anything. You're entirely right. People are trying to combine approaches of these RBMs, like learning wave functions and then using that to sample more in your phase space to generate more data, to create data. The other nice thing, and this is the reinforcement learning direction in combination with experiments, is you might want to do something else. You might want to take a few measurements, and then given those few measurements, you want to ask what is the best measurement I can do next to gain most information. That's a very simple question, and there's also a reasonably simple answer to that. But then you can have this sort of reinforcement learning scheme where you have your computer, doesn't even have to be reinforcement learning, but you can have your computer suggest what to measure next to create a data set in your experiment, but do that in an efficient way so that perhaps you will still need a massive data set, but at least it doesn't have to be 10 times as large as it otherwise would have been.
I see.
Yeah.
Okay, thank you so much. So if there is any more question, I tend to think that making questions via chat is less intimidating than face-to-face, but it turns out to be not the case sometimes. I'll wait a couple of minutes, and then if nobody has any question, then we move to the next speaker.
I'll hang around anyway. If anyone has questions, they can also just chat.
Okay, we have here a question by Daniel. I don't know if Daniel wants to make the question directly to you. Daniel,
I can read the question. Daniel's asking, is there any way of knowing which type of learning is best for each case? Well, I think most often the problem, it's fairly clear which one you would want to use naively. If you want to do some sort of classification, meaning you want to distinguish set A from set B, and you have answers, then typically supervised learning is your answer, or some form of unsupervised learning where if you don't have complete labels. If anything, if your system involves something like a sequence, like doing a few steps, like as a function of time, tuning a parameter, or in the case of error correction, doing moves after moves, then almost always you end up with reinforcement learning, because you need to have this policy, this strategy component where you say, given this state, then do that.
Okay.
Okay,
let's do just one more question, and then we move to the next speaker.
Yep.
So Jonas is asking, can you explain again why you expect performance of classification to be best at the critical temperature?
Yes, I can do that quickly. So there's two places. Okay, the slides are not updating. Let me try to do that without. I think it's best, the concept you should have in mind is finding the most consistent labeling. If I have a data set with no labels, and now I'm going to randomly assign labels, and then I want to check in hindsight, or randomly assign labels and try to train a neural network to learn those labels. If I give you many pictures of cats and dogs and I assign random labels, then at some point you see a picture of a cat and it has the label cat. And the next time you see a picture of a cat and it's almost identical to the first picture you saw, but this time it has labeled dog, you will think, wait, that's inconsistent. This cannot be a cat, and if this is a dog, for example. And so you will see that your network has difficulties learning that, and the performance, quote unquote, of that network will be low. And now the question, of course, is you can keep guessing random labels forever until you hit the correct one, but that's very inefficient. And what learning by confusion does is make use of the fact that you can order it, and thereby you can efficiently or more efficiently optimize your next guess given your current guess. And it's all about finding that correct labeling.
Okay, thank you so much, Ebert. Sorry, Ars,
sure, yeah.
we have to move to the next speaker. So thank you so much, Ebert. It was a great talk.
You're welcome. Yeah, I can answer in chat. Yeah, thanks.
Okay. So our next speaker is Professor Junsuk Rao from Poham University of Science and Technology. Junsuk, whenever you are ready.
Okay. Can you guys see my slide, right?
Yeah, yeah.
Okay. All right, so thank you for inviting me, George, a great conference. So my topic will be today is a more application. So you saw very basic of this deep learning and artificial intelligence from Ebert, the previous speaker. So I show some practical application into this optical design and fabrication and so on. So the title is Inverse Design in Nanophotonics using Deep Learning. So our group is mainly, working on this metamaterial plasmonics and nanofabrication and so on. Main reason I jump into this AI field is, all the design and fabrication, especially in nanoscale. So we rely on the trial and error, and based on our intuition and previous research and some of equation. So the design rule is very limited, and we can try for sure fabrication, so making stop and try measurement and trial and error. But nanofab is too expensive, so we cannot repeat this very many times. So we are limited money and labor and so on. So we have a limited resource. So here today I show some of the example using this deep learning inverse design. So several methods. We use the first one using this GAN. We try to design this 2D image and show the proper optical properties. So what's the best design and what's the parameter for fabrication. And then second one is a similar, but we expanded to material, also added some material selection, not just the parameter. So we can combine the material design and also some dimension. And then also the reinforcement learning for more optimization. So to find the best ideal design. And if the time allows, I show some of example of the Ford modeling. So basically, this guys is discussed in previous talks, so you will see more some practical example. So basically, so I'll skip all the introduction part here, but the main idea is of finding design in nanostructure. So complicated here, like a metal, dielectric, multi-layer, and very sophisticated geometry and three-dimensional structure. So far, we're trying to find the optimization with a lot of time-consuming process. So now we're gonna overcome such a limit. So this pioneering research, so I couldn't include all here, but there are efforts in this nanophotonics field, how to design this split ring resonator and multi-layer, this like MIM resonator, and what's the best for this core shell nanoparticle, and so on. So here, the first example I showed today is using it is conditional DC GAN. So we use this for inverse design. So the main motivation is, can we design some arbitrary nanophotonic structure, not limited to some specific type? So how we overcome this problem, so we make a two-dimensional binary image. So not just dimension. So if we have a 2D image, it's much easier. We can more flexible in terms of design. So for example, input is such as some optical property. For example, here reflection spectrum, like in visible to NIR, and output will be some of the design. So like a V-shaped antenna, and maybe here we already fixed the material like a gold and aluminum, silver. So we fixed that already. But in terms of the shape and actual the parameter, how wide and how long and so on. So this is the input, and so inverse design result will show the how the structural image. And then we make this one by nanofabrication, and we compare with the original input property. We can compare the result. So this is one set of data. So we already fixed the material like a silicon substrate, magnesium fluoride layer, and thickness is fixed, and silver antenna, this is important, and one image of output and one input data of optical property, in this case reflection spectrum. So we have two networks here in CDC GAN. One is generator network. So basically generator network is from noise and input spectrum. So make such as image as an output. So here we can see we have a 4 transport the CNN network, and probably distribution will show the sum of structural image in 2D. And second network is called discriminator. So basically discriminator network evaluate the previous result. So here, this one is come from generator network. So it's made the image, and the upper side is like a target design group we use for train, or some ground truth we use. So this discriminator network compare, this is a good image or bad image. So the result will show the like a 0 or 1, like 0 is a bad one. This is come from generator network, or 1 is like it is conceived this is a good image. And then again, what happened here? Generator network is trying to make a best image to cheat discriminator network, and then discriminator network try to evaluate more correctly. This is a good one or fake one. So these two network is competing. So this is how this CDC GAN make a good learning curve to show that this network make more reliable. So this is a basic competing system here. So here is a tested data. So we use this such a this solid line of a black color. So it's optical spectrum and this trained data. And then this red one is generated image by this AI deep learning. And then we like either do experiment or simulation of this red color data and find the optical property. So this red dot line is come from the this created image. So you can see not actually all like 100% the same, but pretty tendency or like a peak location and depth of this peak is pretty close to the original ground truth. So here like mean absolute error is about like 3.03, so it's pretty good. And then here is some more interesting trial. So like a ground truth is like this like a triangle or star here, but we didn't train this one. So this deep learning AI doesn't know about this model like triangle and star, but this optical properties like here, and then this network is generated suggested image here, H shape or circle. So it's not same as the ground truth. Triangle and H bar is all totally different, but in terms of optical properties, it's pretty same. So in this case, we don't need to only try this triangle shape. We can use H shape also. And also this star is more complex, so we don't need to stick on this star, and this red just circle show the same optical property. So if we don't care about geometry, maybe this is more easier for fabrication experiment. So the result shown here is, due to the non-uniqueness of correlation. So basically, this network does not memorize, does not remember, but they try to understand the relationship between this optical property and this design. So what we did to try more convincing result, so we made like a hand-drawn. So this is a hand-drawn reflection spectrum. So simply, okay, we discussed with a colleague, we need, like a 50% reflection in like a 600 nanometer wavelength. What is the best structure? We can just draw by pen, and then try this with this network. And this red one is, created the image. And then we again, it is predicted response from this image, this structure will be this red dashed line. It's pretty similar, right? So so we can, this is more useful practically. We can use combining with this like a simulation tool, numerical simulation tool and experimental stuff. And one last thing I'm gonna mention is, how we can prove this is like actual learning, not memorizing. So what we did, we did from here, like 9 different images. What happened here, we slightly changed the input noise in the generator network. And while we are changing this input noise, and they try to show the tendency, they slightly moving, change the design. So they learn what it means. They basically learn the correlation. So not just memorizing it. So this is we can claim, like evidence of learning, but some people say maybe not enough this one, but I'm not actually this deep learning scientist, so we are pretty happy. So the second example is a more advanced from the not only the parameter dimension, but also the what material will be the best in our application. So designing material and structural parameter simultaneously. But here the problem is, like a material choice is not continuous matter, like a selection matter, but structural parameter is a continuous one, dimension. So how we solve this one idea is like a material is an index, like number 1, number 0. So it's not the continuous thing. So to apply this material indexing, some like quantized number, we revise the loss function properly to apply this stuff. So here input spectrum is input data is the same optical property. In this case, we do like electric dipole and magnetic dipoles extinction spectrum is the input. And output is like a co-shell design, like a nanoparticle, but like a 3 material combination nanoparticle. For sure, we can do 1 here. Like if T2 and T3 is 0, and only 1 material is happen. But anyway, this is a output result of design, material, and dimension of diameter. So in this case, not like a very complex 2-dimensional design. So the dimension parameter is only radius, so it's a more simplified one. Anyway, here here the commonly we are using material in plasmonics and nanophotonics like silver, gold, and several oxide, titanium oxide, silicon, and we changed some loss function to include this material problem. So material is basically classification, right? So we use the loss function. Overall loss function is divided to spectrum information and design. And this design loss function again includes the structural parameter and material choice. So this is how we try to include this classification problem into in this network. So first network is given here, input data, optical property, and first result is show the design. So this design called like a DN, we like a design network, show the design result. And then another network, like a consequent network, spectrum network is evaluate again. So if spectrum is good or correct or not. So basically these two combination of network evaluate our result. So here, like same need, a previous problem, this is the trained input data, electrical dipole, magnetic dipole, and corresponding material choice, copper, silicon, and the diameter of this T1, T2, T3. And then this predicted response, you can see pretty, follow the tendency. So some of the error happen here, but, comparing, so if you reflect the previous result, it's pretty okay. Like error bar is less than like 0.2 something. So samely, we try to slightly gradually change the input spectrum. So this is to, again, this network is correctly learn the relationship. What it happened, we know like in like UV, aluminum, copper is a more correct material in this plasmonics, and visible, gold and silver is a more proper material. So what we did, started from 350 nanometer, is UV. So you can see aluminum, titanium oxide, and relative thickness is given. So it's correct. And we slightly changed the wavelength, 360, again still UV aluminum, but overcome more than 370, 380, 390, is entered the visible wavelength. Now it's not, it try to intentionally exclude aluminum and more include like gold and silver. So which means they know what happened is in different wavelengths, what's the optical property, epsilon and mu is required for correct application. So this is some of the evidence of the learning. So transition point is about from 375 something, so aluminum to silver and gold. So based on this network, we try like design this like a nanoparticle. So you can see the electrical dipole is given correctly what we want. So magnetic dipole also little more difficult than electrical dipole, but pretty work well. So we designed this electrical dipole, magnetic dipole respectively, and then try to combine this ED and MD together. The reason we need, for example, to design like a negative index medium, like invisibility clocking, we have to deal with this epsilon and mu together at the like same wavelength area. So have to consider ED, MD together. So so far no like a direct application for the negative index medium here, but if this method is correctly applied, we may find this like minus epsilon minus mu structure much easier in this particle system. So this is the based on this GAN network, we show like 2D design and material choice and some of design parameter together. And maybe a few more minutes, I'll show this using reinforcement learning for optimize some given system. So it's called double deep Q learning. Actually started from this Japanese game company, Atari and Google use this double deep Q learning. So basically, reward and reward the system. We give more reward when they are close to the result. So here is like a structure we're gonna optimize: silicon substrate, nitride, and silicon disk, and thickness, pitch, diameter, and thickness of a bottom layer. So using this reward system, we find to try how they can close to the result. So the color in this structural color dielectric metasurface. So our target color is like actually blue. But the first result, the network is shown is like a green, more like this, like a dark green color. And this is not correct, right? But we give a reward, like less reward or more reward. And then based on this reward system, and then next trial, they show different color, maybe a little more blue-green. And then they can close to the target color eventually. So this is like a design method we use in action definition. So here you can see compare. For sure, human or some conventional optimization system can do, So target color is like RGB, and like a final result is similar, right? But the eventual result, you can see out of the 334 million candidate, only 9,000 step is this reinforcement learning found the result comparing the previous optimized result. It's much faster. Just like a few seconds, you have the result. And same thing happened, so you can see, started from here, starting color, and they explore this area, and they feel going to green color is not good direction, less leeward. Red and less leeward. Okay, go to the violet. And then they have more leeward, and they explorate, making more focusing into this violet color, and then eventually they are arriving this target color. So that's how this double dip learning, do this business. So we have a few more application, but I'm gonna skip basically same. How to increase the hologram efficiency. So we demonstrate like a 17% in visible hologram, the best one, but actually that was not best. It can go up to more than double of the efficiency. So it's, this double dip learning model is working pretty well. So okay, maybe no more time for this fold modeling. So I will finish with some conclusion. So we designed this nanophotonic structure in nano, like visible to MIR area. So for more flexible design and included mature choice, and it's pretty work well with the conventional this numerical method and experimental results. So this deep learning assisted inverse design will increase the degree of freedom, more flexibility. But we have making sure we have to consider also fabrication constraint, because many of the structure I showed today is not manufacturable. It's very hard to make. So now we are adding this manufacturable condition into the system, so they can evaluate which one is manufacturable or not. So then will be much more powerful. So here, George and I write some perspective article about this deep learning in nanophotonics. So okay, so sorry for the over the time, so I'll stop here. So thank you very much, guys.
Yeah, thank you so much, Yusuk. It has been a really nice talk. Now time for questions. Questions. So we have time for maybe one or a couple of questions.
Yeah, if anytime if you have question, we can doing this chatting. You can use chat.
Yeah, definitely. Use the chat. Well, again, let me start by making a question. This idea of creating a loss function that is adding more and more ingredients is something that I find quite intriguing. So would you say when you introduce, your fabrication constraint, will you be able to create a loss function that accounts, I don't know, for disorder in the fabrication or whatever effect?
Yeah, it's actually okay. Actually, that's pretty difficult. How we can include this manufacturable condition, so we can include in the loss function. So can you see this, all right? So we actually tried some trial. Maybe this could be classification. So the final result in some structure. So myself, like we have to evaluate this is doable in like even lithography or some of some self-assembly or not. So here, like a nanoparticle, we made it by the self-assembly, but we cannot expect what's the final shape. We have to wait until the final structure is made. So after making this one, so we evaluate like this one is made by certain condition and doable. So we included this fabrication thing into the loss function as a classification problem. So what happened here, if your input is like a wavelength, what's the optical property, and this result will show the final design. and related fabrication process condition, like using which type of like a temperature and which type of photoresist, which type of lithography, and so on. But still very far from the practical stuff. But we can you know should be able to do in near future.
Yeah, very interesting. Thank you so much. Okay, so thank you, Jun-Suk. Thank you for the talk. It was really interesting. So we have now to move to the next speaker of the morning before the coffee break. The speaker is Luigi Bonatti. Hey, Luigi. And he's going to tell us about, he's from ATH, and he's going to tell us about ab initio machine learning potentials for phase transition and phase diagrams using enhanced sampling method. Thank you, Luigi. Whenever you're ready.
Thank you for the introduction. I'm Luigi. I'm a PhD student in the group of Professor Parinello at ETH Zurich and USI Lugano. And today I will talk about how to develop machine learning potential for study complex processes like phase transitions.
Ja, ich habe mich schon gerade gewundert.
I will, is there someone in the background? Okay, so I would like to start with this question. How can we study phase transitions with an ab initio accuracy? The point is that phase transitions, together with many other processes like chemical reactions and biomolecular processes and so on and so forth, fall into a category called rare events due to their occurrences on a very, very long time scale. And this is much longer than what we are typically able to simulate with molecular dynamics, so by integrating the equation of motion. We cannot do it with interatomic potentials, so empirical force fields, let alone with density functional theory. So to bridge the gap between the accuracy of quantum mechanical methods like DFT and the efficiency of interatomic potentials, we can resort to machine learning potentials, which can provide an accurate but also cheap representation of the quantum mechanical potential energy surface using different kinds of architectures like neural networks or Gaussian processes. Still, as you can see also from the picture here, we are far away from the range of timescales we would like to simulate. So we need to resort also to another kind of methods, which are called enhanced sampling, and they are a family of techniques devised to bridge the gap between the timescales of simulations and the one of experiments. Let's start by briefly going through the generation of machine learning potential. It's an instance of supervised learning. So the first step is the construction of what is called a reference database, which consists on a set of configurations, and their labels are energies and forces, typically computed at the DFT or beyond level. And once this is done, and I will go back to this soon, we need to convert the raw atomic coordinates into symmetry invariant descriptors, because we want our potential energy surface to be invariant under all the natural symmetries. Finally, one can do the actual fitting of the potential. So in the last few years, there have been really a lot of development towards both the atomic environments and the fitting architectures. Here we just use one of them, which is called Deep Potential Molecular Dynamics, DeepMD, developed by Zhang and other in Princeton. And it uses neural network to predict each, it decomposes the energy into the sum of local contributions, and which is predicted by a neural network. I don't have much time to enter into all the details, so you can ask about this later if you want. And let's go back to the first step, which is actually one of the most important ones, the choice of the construction of the training set. And the reason why this is a very critical step is because neural networks are known to be good for interpolation, but not as good for extrapolation. So let's say we want to study a complex process. let's say, for instance, liquid to solid transition, so crystallization, we cannot simply provide liquid and crystalline structures. We need to provide also all the important interface between the different phases and maybe defected configurations. And a priori, one doesn't know how this process goes. And so this is very difficult. So it's clear, and this is the first take-home message I would like to convey, is that equilibrium configurations, which is what is typically done in order to train these kind of neural machine learning potentials, are not enough to build a potential to study complex out of equilibrium processes. A possible solution could come from enhanced sampling methods, which are a way to sample all the relevant configuration for a process of interest. So I said enhanced sampling methods are designed to accelerate rare events. And among them, we find a family of methods which is based on collective variables, which means once one chooses a few important variables, let's call them order parameters or collective variables, which are connected to the process of interest, and enhance their fluctuations by adding an external potential, V, in addition to the potential energy of the system. Two examples of this family are metadynamics, which is a very well-known and established method developed almost 20 years ago, and in which this bias potential V is made up of Gaussians centered at the visited points. Another more recent example, which I will use also later, it's called variational enhanced sampling. And in this case, the bias potential is defined upon a variational principle. And as you can see also from the movie, while when one run molecular dynamics run, if there is a rare event, this means that the system won't be able to escape from the local minima and to reach maybe the global one. While by adding this bias potential, we are able to identify all the relevant metastable minima and also to sample the transition pathway. So it's clear that these kind of methods can be used not only for the study of the process of interest, but also as an efficient way to sample the relevant structures. Let's go into the first application. We studied silicon crystallization, and this is very, very difficult to study from first principles, so with the accuracy of quantum mechanics. And for two reasons. The first is the very long time scale at which this process happens. And the second is that there is a subtle interplay between covalent and metallic behavior between the liquid and the crystalline silicon, so which requires for an ab initio description of the interactions. So in this case, in order to collect the configurations, we did the following. To cover the equilibrium configurations of the solid and the liquid, we ran a short ab initio BFT-based molecular dynamics simulation, very short, it's about 5 picoseconds. And then to cover all the other important configurations, we ran classical molecular dynamics simulations using an empirical potential accelerated with metadynamics. And as order parameter, as collective variable, we choose something connected to the bistructure factor to promote the liquid to solid transition. And this is the result. So this is the histogram of the configuration sampled during different molecular dynamics simulations. The red and the blue are standard molecular dynamics simulations starting from either the liquid or the solid. And the orange curve represents the configurations sampled in a single metadynamics simulation. And it's clear how metadynamics allow to sample the intermediate states that, although metastable, are crucial for the transformation. And so we are able to sample a very wider region of the phase space. And this can only make our potential more robust. So after we collected this configuration with a classical potentials, then we labeled at the ab initio level using DFT. And then we can train with these configurations and their labels, energy and forces, we can train the potential. And actually here it's just worth to say that we are able to to obtain a very good accuracy over a very wide range of energies. This is about 1 electron volt per atom. And on the right, you see how also the radial distribution function of the two phases is very well described. Once we have developed such potential, we can use it to study many properties of crystallization. So here on the left, you see a trajectory of a metadynamic simulation done with our neural network potential, in which the system is reversibly driven between the liquid and the solid. And the time scale is very long. It's 400 nanoseconds, which if we compare to the timescales which we are limited with in the case of DFT-based MD, which are a few picoseconds, is really a huge speed up. And from these simulations, these enhanced sampling simulations, we can then recover the free energy profiles, which allow us to study the relative stability between the two phases, the liquid and the solid, and also to compute, for instance, the free energy difference as a function of the dependence of the free energy difference on the temperature, which allow us to extract a lot of interesting thermodynamic properties like the melting temperature, the entropy and enthalpy change upon melting, as well as dynamic properties, which with a very good agreement also with experiments. Then we have a second application, which is gallium. This work has been done in collaboration with Yang Niu and Pablo Piaggi. And we decided to take this approach of using enhanced sampling to build neural network potential a step further. And so going from the study of a single liquid to solid phase transition to the study of an entire region of the phase diagram. Gallium features a lot of interesting properties. It has a very low melting point. It crystallizes in very complex structures, which again feature the coexistence of covalent metallic bonding. So it's also much more difficult than the previous example. And since here our aim is more ambitious, we want to collect configurations from a very wide pressure and temperature range. And again, we can do this by resorting to enhanced sampling methods, in particular to one which allows to sample in a single simulation the multi-thermal multibaric ensemble. And this can be done by using the variation sampling method together with a tailored order parameter to promote the liquid to solid transition between each relevant phase. As before, this picture illustrates the range of configurations sampled in different ensembles. The circles represents standard thermal isobaric simulations at different temperature and pressures, while the points represent the configuration sampled during a single, this is important, a single multi-thermal multibaric simulation. And as you can see, it really allows us to sample a much wider phase space region, first point. And the second, which I think is very important, the usage of multi-thermal multibaric simulations allow us to clearly defining the range of validity where our neural network potential can be trusted. So from this temperature to the other temperature, from this pressure to the other pressure. And this is important because with neural network, we have no direct control over the uncertainty of the predictions. So since gallium is a more complex system, it has many complex polymorphs, and this required more iterations. And we can do this with an active learning optimization, which means we started, as in the case of silicon, with a classical force field. We ran multi-thermal multibaric simulations. We extracted the configurations, we labeled them, and then we trained a first version of the potential, which is being later used to generate new configurations. Now only a few of them are selected for labeling and retraining in order to improve the potential. And after a few iterations, we obtain a robust and reliable potential over a very wide pressure and temperature range. We can use it to study the phase diagram, which shows a good agreement with experiments. And we can also, more importantly, we can use it to study at the atomistic level the nucleation process. This is homogeneous nucleation. And so here you can see for two different phases, which are the most relevant at low pressure, the alpha gallium and beta gallium, the nucleation, a few snapshots from the nucleation process. And as you can see, the shape of the nucleus is roughly spherical. And this allows us, together with other things, to study this process under the framework of the classical nucleation theory. And for instance, we can compute a lot of interesting properties. Here we see the critical nucleus size as a function of the temperature for the two phase. And you can see that the one of alpha gallium is consistently lower than the one of beta gallium. However, by putting all the ingredients together, we see that above 174 Kelvin, the alpha gallium phase is not the most stable. Rather, the undercooled liquid gallium crystallizes into beta gallium. And this is in agreement with experiments and wasn't something which wasn't explained before. And furthermore, we can compute the nucleation rates. And as you can see, they are very, very small numbers. So if you take the time needed for observe such a process will become very, very huge, probably more than the time of the universe, at least according to this number. And this explains why homogeneous nucleation cannot take place under these conditions. And in agreement with experiments is indeed the heterogeneous nucleation, which is expected to be the normal crystallization mechanism. And also all these results and these very huge characteristic times indicates why the liquid gallium can be undercooled to extremely low temperatures. How is it observed? The last, very last example is about how to develop machine learning potential for chemical reactive events. And we are studying urea decomposition in water. And here, the problem of how to construct the training set is even harder, because it's clear that in order to teach a neural network a reactive event, we cannot just provide configurations from the products or the reactants, because we need to provide all the different transition states and metastable states from which the reaction has to go through. So in this case, in order to develop our neural network potential, we started, rather than from a classical potential, from a short ab initio molecular dynamics run with metadynamics to obtain the reactive configurations. And then, as before, starting from a first version of the potential, we did a few iterations using an unsampling at different temperatures in order to build a reliable potential. And this allows us to study, for instance, the reaction mechanism. So for instance, here you see the free energy profile as a function of two order parameters, even at low temperatures, and also to study the kinetic rates in a very wide temperature range. And these, both these things weren't possible otherwise with ab initio molecular dynamics, because at low temperature, the rates increase exponentially, as you can see here in this picture. So just to conclude, I think the take-home message is, which I hope I exemplified, is that equilibrium structures are not enough to building accurate potentials for reactive processes, like phase transitions or molecular reaction or chemical reactions and so on. A possible solution to this can come from enhanced sampling methods, because they are specifically designed to sample this relevant configuration for the process of interest. And all of this is worth because it opens up the way to explore fascinating physics, which take place at very long timescales, with accuracy of quantum mechanics. And for instance, I show you the silicon, the crystallization of silicon, and most importantly, because I think it's more interesting, also the gallium nucleation mechanism. I would like just to conclude by thanking my supervisor, Professor Parinello, and all the other collaborators I work with, work represented here. And thank you all for the attention.
Okay, thank you so much, Luigi. Time for questions now. You can use the chat to make your question.
Yeah.
Let's see if somebody have any question. Okay, you have a question by Eliska.
Yeah.
Mhm.
So, okay, like here, actually I have.
Let me read the question for everyone. So Eliska is asking if you could talk a bit more about the architectures you have used in the respective case you saw during the talk.
Yes. So let me. So in this case, the idea is that we need to build our potential energy surface, which needs to be invariant under rotation, translation, and permutation. So in order to enforce the rotational and translational symmetries, we need to convert the atomic coordinates into some descriptors. While in order to enforce the permutational symmetry, this is achieved by using a different neural network for each atomic energy, and with weight sharing between them. So if the neural network which predicts the energy of two atoms of the same chemical kind are constrained to be the same during the optimization, and then all of them are summed up. And these energy decompositions allow to train the system on, this is done because it allows to train the neural network on a small system and then use it also for large systems. So the architecture of each sub-neural network is just a standard feed-forward neural network with a few, typically what I use here is 4 to 5 layers with a number of nodes going from, let's say, 200, 100, 50, 20, 10, 5, something like this. So it's quite big. And the loss function is just the mean square error on the energy, the forces, and the virial, if present, given by some prefactors. So the idea is that for each configuration, we have 1 energy and 3 n forces. So it's this is something which can be tuned so the prefactor of the mean square error on the energy and the forces can be optimized to change during the training. And that's it, I would say. If there are any more questions, I will be happy to answer later in the chat.
Yeah, thank you so much, Luigi. We are a little bit behind the schedule, so yeah. Let's wrap this part of the session here, and we will make a break of 12 minutes until 11:15, if that's okay for all of you, and we get back sharp at 11:15. Thank you so much for attending this part of the session, and let me thank to all the speakers of this part of the session. Thank you so much.
Hi everyone, I hope you can hear me. My name is Eliška. and I am going to chair the second half of the session. So in this session, in the second half of this session, we will have 3 more talks. The first one is by Anna David from ICFO and University of Warsaw, and she will tell us about phase detection with neural network. She is already sharing the screen, so please, Anna, go ahead. You can start your talk.
Thanks, Eliška. I'm very happy to be here and excited to present you the results of our project. I'm a PhD student in the group of Professor Maciek Lewenstein and at ICFO and Dr. Michał Tomza at the Faculty of Physics at the University of Warsaw. And we aim to answer the question, like general question, what really machine learning models learn in phase classification problems. So we want to interpret the neural networks, the black box of neural network. As I said, it was teamwork. So the main mastermind behind all this is Dr. Alexander Feng from ICFO. We executed the project along with Patrick Wembeli and under the supervision of both Professor Lewenstein and Dr. Tomza. So my main aim is to present you a very general universal tool that should allow you in any machine learning model you use in a supervised setup, in any actually problem you're dealing with, but we will focus on the phase classification problems, that should allow you to get an insight into your machine learning model. So we try to answer the question what it learns, as I said. To present you this tool and to convince you of its usefulness, I will start with the short introduction to the machine learning in phase classification. It will be short because thankfully I'm not the first one in this sessions, and already the speakers before me they did a great job of introducing the subject. Then I will talk about the interpretability of machine learning and the method especially. Then I will shortly introduce the physical model whose phases we want to analyze. In general, it can be any physical model, but we focused on the Fermi-Hubbard one. And then I present you the results. So we all know these 2 papers probably, and we had the pleasure of listening to the first author of this paper. And these 2 articles really kicked off the field of which uses machine learning based algorithms to classify phases of matter to detect phase transitions. And this idea proved to be very fruitful. And this is a really subjective choice of papers that is supposed to just to prove it's a very abundant field. However, so far, this approach has mostly enabled only the recovery of known phase diagrams, and we should remember that. The agreement with more conventional approaches was only qualitative usually. However, this machine learning tools proved to be very, to have a much lower computational cost than this conventional approaches based, for instance, on order parameters. But we haven't really learned new physics yet from this approach. And moreover, there are still open problems. So machine learning algorithms have troubles with detecting quantum many-body localization, for example, or topological phases of matter. And we do believe that with introduction of interpretability tools, we may also gain insight why our machine learning algorithms fail in these tasks. So this is our main aim and motivation. So we want to answer the question, what really machine learns in the phase classification problem, and there are 2 options basically, right? So first of all, it can correctly learn the order parameter. If yes, then great. We can give you a tool that gives you a hint that it's really the case. And this is really good. We want to be confident. We want to trust the machine we're using. But it also can be that the machine learns something else in order parameter. It can learn some something accidental. It can be some background, and it falls. I mean, it gives you good results in your data set, but actually it wouldn't work on very different data. So this is also good. We want to be sure that whether we can or cannot trust the machine, and we should worry about that. But also we can maybe see that, okay, it doesn't learn order parameter as we predicted, but maybe it learns something still meaningful. And these are the 3 outcomes that we want to study. And our results will present you, especially these 2 positive ones. So moving on to the interpretability of machine learning. So in general, interpretability is the ability to explain the predictions, the explicits, the outcomes in a way understandable to a human. So far, most of the machine learning models are black boxes. So we just put something inside, we get some answers, and the mathematical complexity of these models is just too great for humans to grasp the, let's say, the decision process behind that. And also we know that we shouldn't really, we have proof that we shouldn't be blindly trust machines, because it was shown that even that in the case of image recognition, even small changes imperceptible to a human can completely change the predictions of the machine learning models. For example, you add some pixels, you change some pixels in the tomato picture, and you get the prediction it's a dog. And also it was shown that machine learning algorithms inherit biases badly from humans preparing the data. So we just know that we shouldn't. So these are all arguments that should show us that we cannot blindly trust the machines, also in physical problems. And here are so this is the idea of how to check what it really learns, to have some arguments that we can trust our model. The interpretability method is called Libo-Node training. This is the first step towards our method that I'm going to discuss. And this is a way of understanding how your training data impacts the predictions. And this is, I think, very intuitive way of testing what your network learns. So imagine you have your n training points. You find the minimum of your loss function, and you have some test loss. So the value of your test loss. And then you imagine you remove one of these training points. Now you have one less. You retrain your machine, and you again get some test loss. And you have 2 options. Either this test loss now it's higher than it was before, so the machine is less certain about the prediction. This means that the removed example was a helpful one. And opposite, if the test loss gets lower, that means that, and so the machine is more certain about this prediction, let's say, it means that the removed training point was a harmful example. So with this, we can kind of trace the decision, like the reasoning process, let's say, of the black box, and we can judge how influential every training point was for a single prediction. And with that, it can give you some information. Problem with this approach, I mean, this is very old approach, it's starting from the dawn of machine learning, it's super expensive. So because so usually you have data sets of thousands or even tens of thousands points, and you would need to retrain as many times as you have training points multiplied by an amount of your predictions. So this is super expensive. So this is finally the tool we want to convince you to use. So this is a tool called influence functions. It was designed in the 70s already, and it's an analytical approximation for Libo-Node training. So using Taylor approximation, you can judge whether the removal of this one single training point would be harmful or helpful, would decrease or increase the test loss of the single prediction. There is one numerical trick. I don't want to go into details, but to calculate this approximation, you need to calculate the Hessian of the training loss of your model. And as we probably know that neural networks and any deep models are very non-convex models. So you would need to generalize to that, and it was done by Koch and Liang. And actually, this guys really introduced this influence functions to modern machine learning. And this is the images coming from their paper. They kind of gave us the intuition how this tool work. So you calculate the influence function for the test image. That here is the clownfish. And they calculated the most helpful examples for this prediction. So there are two different machine learning models. This is let's say, we are going to the details. This is like simpler machine learning model, and this is very complex machine learning model. And these two aquatic creatures proved to be the most influential, the most helpful for the single test image when the simpler machine learning model was predicting the class. And these two pictures with clownfish were the most helpful ones when the inception neural network were predicting the test image. So they were, with this, you can kind of judge the, okay, so the simpler model mostly learned the background, and maybe the water was the most influential factor in decision process, while the more complex model really learned the properties of the clownfish. So this is how you can judge the sensibility of your network. So we want to try that approach in the phase classification problems. As I said before, you can use it to any problem you want, especially any phase classification problem you want. But just a proof of concept, we used it in the spinless Fermi-Hubbard model at half filling. So you have particles; they can hop between sites. They interact with their nearest neighbors and next nearest neighbors. So I think this is enough for that. And this is the phase diagram of such a model. So you have here this uniform phase where particles are smeared out across all sides. This is Luttinger liquid phase, and we're gonna look at that. So just keep it in mind. And here you have the charge density wave 1, where, as you can see, there is this rigged occupancy of the sites. Bond order is the phase that has a staggered hoppings between sites, and there is the charge density wave 2 with different pattern of the mean occupancy. And this would be the order parameters for this phase for these phases here. So now I'm gonna show you the general method to analyze what neural network learned in the phase classification problem on the example of this Fermi-Hubbard. You're gonna see two setups. So firstly, we analyze this transition here with the arrow 1. So from Luttinger liquid to charge density wave 1. And we will follow with this analysis across 3 phases. You're gonna see a series of pictures like this. So what does it mean? The y-axis are the influence function values of the training points here for the single prediction, and they're across the transition across the phase transition. So here we have, with this shading of the background, we have the transition point. So here we have Luttinger liquid, here we have the charge density wave 1. Here are the training examples from the phase 1. So here the charge density wave 1, and here training examples from phase 0. This is the prediction for which we are calculating all these influence functions. And here are the most helpful training examples for this prediction. And these are most harmful training examples for this prediction. So this would be the main idea of that. Okay, so as I said, we are looking at this transition. So this is between the uniform phase and this staggered phase, which occurs when you increase the nearest neighbor interaction. And what we should see if the machine learning model learns an order parameter. So the order parameter here is 0, because the order parameter is the difference between mean occupancies between neighboring sites. And here, the order parameter on this side grows from 0 to 1, right? So if the machine learning model learns order parameter, all training points from the phase 0 from the Luttinger liquid should be similarly influential because they all have similar order parameter, right? And on the other side, the most helpful points should be the ones with the most similar order parameter. So in the vicinity of the prediction. And we can see exactly that. So this would be the picture we would expect from the model that learns order parameter in this problem. So this is the first thing. We can gain the trust in the model with this approach, but we can also see, let's say, new physics there. So to show that, we convinced the machine that we labeled now we studied this transition. So between Luttinger liquid through bond order through charge density wave 2. And we said to the machine, okay, these points from bond order and charge density wave 2 are one phase. But with this influence function, it does see that these points are completely different, okay, are significantly different than all the other from here. So it kind of detected the additional phase in the training data, even though the predictions were still okay. So the predictions in this phase was that it's phase 1, it was phase 0, but we have additional information coming from this tool. And this was the opposite. We labeled all this bond order and Luttinger liquid as the phase 0, here as phase 1. And this is what we see when the machine learning learns something, when machine learning models learn something silly, because here you see the signs of overfitting. So this would be the result you don't want to have, and this is what should increase your distrust to your model. So this was a really rapid summary of what we showed. There we have more nicer results as well. But I hope I convinced you that there is a nice interpretability tool that you can use for your machine learning setups called influence functions. And I hope I convinced you that we really need such tools in science. It should allow you to search for unknown order parameters, help you to search for unknown order parameters in different phase classification setups like MBL or topological models that we know that machine learning has problems with. And if you have interpretable neural network, it can detect unknown phases. So we hope that this tool can also allow you to distinguish between types of phase transition, like first order and second order, and we are gonna apply it to different to classify experimental data. And thank you for your attention. Sorry for being a little too late. This is the paper that we published all our results, and I welcome all the questions that I'm not able to answer right now via email. I will be happy to answer. Thanks a lot.
Thank you very much, Anna, for a very interesting talk. So I again invite everyone to type their questions into the chat. Hopefully, while some questions are coming in, let me just start by asking this function that you calculate to evaluate the training points. Can you just show the formula one more time? I didn't get all the terms. Is it always easy to calculate this thing? Is it always smooth? Is it possible to evaluate simply numerically?
No, so yeah, of course there are, I mean, this is I swept a lot under the carpet. This is not super easy. I mean, okay, so in principle, it's not that hard. What you need is the gradient of your test loss. So it's not that bad. You need a gradient of the training loss, but built only on your one removed training point. So it's also not bad. Part is this: you need the inverse of the Hessian in the minimum of your training loss. And this is tricky because if you want to have the Hessian, the inverse of the Hessian, it needs to be positive definite. So it cannot have any negative eigenvalues or eigenvalues close to 0.
Right.
the case with neural networks, of course. So there is this generalization that was done by Koch and Young, and they just add a term, like they call it a damping term, that just, it's a constant term to put all eigenvalues to make them larger. And this conserves all the, what is most influential, what is least influential. But I mean, the relationship with leave one out training is a little disturbed. So it's not 1-to-1 ratio, but the relative influentiality of the point stays the same. And also this Hessian can get really big with huge neural networks. So there are ways of approximating them. But I think that for now we're dealing with not such large neural networks with, let's say, parameters of order of thousands, and then you can calculate the Hessian exactly, and that's what we do. But if you have like 8 million parameters that you need to, for example, use a stochastic approximation of this Hessian, because otherwise it's impossible. You don't have program to do that.
Okay, thank you. Let me continue with reading. We have questions from Evert van Nieuwenburg, who is asking, in the case when your machinery learned a silly model, you mentioned that you saw signs of overfitting. Is that how you would detect whether the model is silly, or are there other ways of knowing when to discard a learned model?
Because when I'm saying silly and not silly, I already mean that you like analyze your test set, right? I mean, like your validation set and your test set, and you think, okay, it looks like my model makes sensible guesses because I know the answers for the test set and it gave the matching answers. But for example, we can play with this assumption and say, okay, the test and validation sets and training set, they all come from the same domain. They're all similar. And in real life, we're going to use it to the data that are a little different than that. And we have no way of checking whether the answers to the questions we don't know answers for are really matching. And so I would say this is a good way of judging whether your machine learning model will generalize well. Because if it doesn't learn the order parameter, let's say the quantity you're expecting it, then probably it will give you silly answers. And why I'm saying it's a sign of overfitting. Okay, so this is the bond order phase. This is Luttinger liquid phase. We said this is phase 0 for this is the single one phase for this setup, and this is the Chudovsky wave 2. So there should be just one order parameter guiding this transition. It should be 0 here, and it should be slowly going to 1 on this side. But you see that all these points are similarly influential, and here you don't see this, let's say, expected behavior that the most harmful points are following the line. So I would say this is enough of the, let's say, maybe it's not a proof, but it's a sign you should distrust and the model, and it's a sign that it is a silly model and didn't learn the order parameter, because this is what I would like to see in the setup when we have order parameter 0 growing to 1. So I want the curvature of the influence function values of the training points to follow a little curvature of the order parameter. And I hope that we kind of, okay, thank you.
So we are actually running a little bit behind the schedule, but we have two more cool questions about like relating the training set to the architecture properties and the properties of the phase transition. So maybe let's, as an experiment, Anna, do you think you could later answer in a chat, or you can just like connect further in a private messages?
Of course, I'd be happy to.
With that, let's thank Anna again, and let's move on to the next talk.
Thanks a lot.
Thank you. Mohammed, can you go ahead and start? Perfect. So our next speaker is Mohammed Hebat Allah from Vector Institute in Toronto, and he will talk about neural simulated classical and quantum annealing. Welcome, Mohammed. Please go ahead.
Oh, thanks very much, Eliska, for the kind introduction. Can you hear me first? Is it clear what I'm saying?
Yeah, we can hear you.
Oh. Okay, cool. Can you also see the virtual laser pointer And
Lazy
also,
pointer is working, yeah.
can you also see like if I'm writing something in the screen? No. Can you see like if I'm writing something on the screen?
Now it's something written. Yeah.
Okay, cool. Thanks. Sorry about that. Yeah. So hello everyone. I hope you're all doing well. So my name is Mohammed, and today it's my great pleasure to talk to you about our recent work about how we can solve optimization problems using both the power of neural networks and simulated annealing, both classical and quantum. But before starting the talk, I would like first to thank the organizers for giving me this wonderful opportunity to speak here. And I would like also to acknowledge my collaborators, Estelle, Roland, and Juan and Roger, who deserve a lot of credit for this work as well. And I should mention that the results I'm going to mention in this talk are not published yet, but hopefully they will appear soon on arXiv. So I think a good place to start with in this talk is with the unfortunate fact that many real-world optimization problems are very hard to solve. And this is somehow related to the curse of dimensionality in those problems, where if you take a typical optimization problem and you try to solve it using a brute force algorithm, then the running time increases exponentially with the system size until it eventually reaches a time that's comparable to the age of the universe. So that's something not practical at all. And hence there is a need for some new algorithms that would help us to push this exponential tail in the running time to further and further larger system sizes so that we can solve practical problems within a reasonable amount of time. And this talk will be a step forward toward that goal. So I'm going to show you a new way to solve optimization problems using artificial neural networks, in particular, using recurrent neural networks by taking advantage of simulated annealing, both classical and quantum. And for this purpose, in the first part of this talk, I'm going to show you how we can use recurrent neural networks to find ground states of quantum many-body Hamiltonians. And this will lead the foundation for how we can simulate a variational version of classical annealing with RNNs. And then I'm going to show you how we can also simulate or implement a variational version of quantum annealing using the same architecture. And at the end of the talk, I'm going to show you some concrete results on how we can use those two methods to find the ground states of two-dimensional spin glass models. Okay, so let's start with the first section. So as you may know already, recurrent neural networks are very essential components of the field of natural language processing, and they have laid the foundations for very interesting technologies like speech recognition and machine translation. And what's interesting about these architectures is that we can also use them to find the ground states of quantum many-body Hamiltonians, as shown in this recent paper, where the basic idea is that you can take a recurrent neural network, which you can think of very simply as a black box with some parameters that I'm metaphorically denoting by this knob here. And the goal is to minimize the expectation value of the Hamiltonian of your interest in the RNN wave function here. And we can do that by taking gradient descents so that we can minimize this expectation value until we achieve convergence, where we expect to get an approximation of the ground state as well as the ground state energy of this Hamiltonian. And this approximation depends on how expressive your recurrent neural network is. And if you're interested in reading more details, you can check out this paper, but pretty much all the details you need to know to be able to follow me are mentioned here. Okay. So now how we can use these architectures to simulate a variational version of classical annealing that we call VCA. So as you may know already, annealing is a very old concept in metallurgy. So if you want, for instance, to build a very strong metal, what you do is you take a metal, you heat it to very high temperatures, and you let it cool very slowly until you achieve an energetically favorable configuration. So in some sense, this procedure is an optimization algorithm, and that's what inspired the simulated classical annealing algorithm, whose goal is to find the minimum of some classical Hamiltonian that can take this form over here. And the way we do that is by minimizing the free energy by introducing thermal fluctuations that would help us to overcome local minima of the Hamiltonian we want to minimize. And the way we do that is by starting from some initial temperature T0 and decreasing it using some linear schedule, for instance, until 0 temperature to find the minimum of this Hamiltonian we want to minimize. And now the question is, can we do the same thing, but now in a variational framework using recurrent neural networks? And one way to do that is by taking the free energy as a cost function that we can minimize, that we try to minimize using gradient descent. So here what we do is we take the expectation values in particular over this Hamiltonian term and also over the entropy. We take those expectation values over the RNN probability distribution. So initially, when the entropy term is much more dominant compared to the Hamiltonian, and we want to minimize, then the free energy as a function of the order parameter of the system is expected to be rather simple, where the minimum corresponds to disordered configurations at high temperature. And then initially, when we take our RNN probability distribution and that's randomly initialized, it's not expected to be at the minimum. So in order to bring it back to the minimum, what we do is we do a couple of gradient descent steps. And then as we decrease temperature, as we do in simulated annealing, we might encounter some phase transitions. And there, the free energy landscape might also change. So in order to bring the RNN back to the minimum, we just do a couple of gradient descent steps. We do as many as we can so that we achieve the minimum. And then as we move forward to 0 temperature, some new minimum might appear, but hopefully as we are close to the minimum, we can just do a couple of more gradient descent steps to achieve the minimum of, to find the ground state of our problem we want to solve. And as a proof of principle for this method, let me show you first a simple experiment on the ferromagnetic Eisen chain with 20 spins. So here what we do is we start from a temperature equal to 2 and we slowly decrease it to 0. And what you see here in this plot is that the free energy calculated by the RNN using our VCA method matches the exact free energy of the system until we eventually find the exact ground state of the system at 0 temperature, which corresponds to all spins being up or all spins being down. Okay, so now before showing you how this method works on a more challenging problem, let me first explain how we can also simulate a variational version of quantum annealing using RNNs. So as you know already also, quantum annealing is the quantum version of classical annealing, which we can implement on a quantum hardware. So initially what we do is we take a quantum state and we prepare it at the ground state of some, what we call a driving Hamiltonian, which can take this form, where we apply a transverse magnetic field on all the spins in our system. And then we time evolve this quantum states by decreasing the magnitude of the magnetic field while increasing the magnitude of the Hamiltonian we want to minimize. And we do this in a sequential manner. So if you do this procedure very quickly, then especially at the minimum gap of the system, you might jump to excited states. From there, you might be likely to get trapped in a local minimum. But if you do this procedure in a more adiabatic fashion, then you'll be more likely to stay at the ground state level. And there you'll have more chance to have the ground state, to obtain the ground state of the Hamiltonian we want. Okay, so now can we do the same thing in a variational way using RNNs instead of doing it on a quantum hardware? And that's actually what we tried in our work. So a way to do this is by taking an RNN wave function with some random parameters, and then we can take couple of gradient descent steps to find the ground state of this Hamiltonian. And then what we can do is we decrease the magnitude of the magnetic field while keeping the parameters of the RNN fixed. And this will result in the fact that the RNN energy will be slightly off the new ground state level. So to correct for that, we do a couple of gradient descents more to bring the RNN closer to the new ground state level. And then we decrease again the magnetic field. And then while keeping the parameters of the RNN fixed, and then we do gradient descents. And then we just keep repeating these steps until we eventually arrive at the ground state of the Hamiltonian if we do this procedure slowly enough. And as a way to illustrate this protocol, let me show you here a simple experiment on the same model. So the ferromagnetic Eisen chain with 20 spins. And here what we do is we start from a magnetic field equal to 2, and we decrease it slowly to 0 magnetic field. And what you see here is that the residual error, which is the difference between the RNN energy and the exact ground state energy at each value of the magnetic field, is much lower compared to the gap of the system, which means that the RNN is always below the first excited states. And this means that the VQA, or the variational quantum annealing particle, can be adiabatic. Okay, so now let's see how we can test our VCA and VQA method on a more challenging problem related to spin glass models. So as a benchmark, we choose a 2-dimensional spin glass model called the Edwards-Anderson model with system size 10 by 10. So here in this model, every 2 neighboring spins are connected by a coupling that's randomly sampled from the range -1 and 1. And what we do is for VCA and VQA, we decrease the temperature and the magnetic field to 0 within a variable number of steps that's represented in the x-axis of this plot here. In the y-axis of this plot, we represent the residual energy per spin. So here the residual energy is defined as the difference between the RNN energy at the end of the annealing minus the exact ground state energy of this model, which we can know in a polynomial time. And what's interesting here is that as we do a lot of steps during our annealing protocol, we see that the residual energy goes down, which means that being adiabatic is a very important component of these algorithms. And what's even more interesting is that we see that the variational classical annealing implementation is much more powerful compared to the quantum implementation. Although we still don't have a clear understanding for why that's the case, we look forward for potential answers in the future. So now, since VCA is much better compared to VQA, we compare it with standard optimization methods for a larger system size. So here we do it for 40 by 40 lattice. And we compare it with 2 methods. The first one is simulated annealing, which is a multicolor implementation of classical annealing. And we also compare with path integral quantum multicolor, which is a multicolor implementation of simulated quantum annealing. And for these 2 methods, we plot the residual energy per spin as a function of the number of multicolor steps I denote here by MCS. And that's basically says how many steps we do, how many multicolor steps we do to decrease temperature or magnetic field to 0 while we do annealing. And what's pretty cool here is that we see that the variational implementation of classical annealing outperforms both simulated annealing and the QMC implementation with almost 3 orders of magnitude. So although we don't have a rigorous explanation for why that's the case, I think a potential answer might be in the fact that VCA, which is based on RNNs, uses a more enhanced sampling technique that's called autoregressive sampling that produces independent samples as opposed to metropolis sampling, which suffers from the problem of autocorrelation. So I think my main takeaways from this talk is that we can use RNNs to wave functions to emulate the behavior of classical and quantum annealing in a variational way for the purpose of solving optimization problems. And throughout this talk, we saw that variational classical annealing is superior compared to variational quantum annealing, and this is yet to be understood in future research. And we saw also that the VCA is superior to both simulated annealing and path integral quantum multicolor on the Edwards-Anderson model. And I think my main takeaway from this talk would be that these new implementations of VCA and VQA might be a potential way to solve real-world optimizations in the future. So that's pretty much all I wanted to talk about today. Thanks very much for your attention, and I'm looking forward to answer your questions. Thank you.
Thank you very much, Mohammed, for your talk. Okay, I invite everyone to start typing their questions in chat. While they do, I will ask like a super naive bigger picture question. So you have chosen RNNs here, and I know that like some like more like old-fashioned way, or like how this field started was to use RBM, for example, for this ground state search. Can you comment a little bit on the structure that RNN has here that specifically helps you with this VCA things?
Yeah, it's a very good question. Yeah, there's no naive question. That's actually a very good question. So I think there's, yeah, I'm glad also you asked, because like there's a reason why we use RNNs. And that's because it's based on autoregressive sampling. So as you know already, like RBMs are based on metropolis sampling, which suffers from autocorrelation. And that's especially a very serious limitation when you're dealing with spin glass models, because there you suffer from the autocorrelation time, which might be a limitation. But for autoregressive sampling, that's not the case, because you can produce independent samples. And that's like, for those who are not specialists with RNNs, basically what we do is we generate spins in a sequential manner by starting from the first spin and then at the last spin using sampling from conditional probabilities. And this procedure will allow us to generate a lot of spins in parallel, and this will allow us to generate a lot of spins that are independent, as opposed to metropolis, where you have to do this in a sequential manner. So I would say that's the main reason why we choose RNNs over RBMs, because of this big advantage.
Okay,
Yeah.
so it's sampling. I see. That's very interesting.
Yeah, does that answer your question?
Definitely, thank you.
Okay, thank you.
Do we have anything else? Looks like people cannot think quickly of anything. So then I invite you to write Mohammed in a private or public chat later if you think about anything else. And in the meantime, thank you for your super nice talk, Mohammed.
Oh, thank you, Aliska. Appreciate it. Have a good day. Thank you.
So our next speaker to close this session is Una Kim from Cornell University. Una, you can go ahead and share your screen now. And Una is going to talk about machine learning for quantum emergence. Welcome, and please go ahead.
Okay, thank you very much for inviting me to this wonderful conference. Let me see if I can get my pointer going. All right, so I want to talk about interpretable machine learning of quantum emergence, and you can find some details of this work, especially the first part of the work in this preprint. So the community of condensed matter physics have been driven by trying to extract more and more information from the material systems that we have, because the content of the material, the information in, for instance, in this compound cadmium rhenium oxide, when you just think about the formula itself, it is very small. The information content is small. But if you think about all the distribution of electron density, or the defects, any faults in the system, the information content can quickly grow to be very extensive. And you can easily compare information content in a crystal of a single crystal of a real material to more than, many times more than the total information content of Library of Congress. So the quest in the community has been to try to extract as much information as possible using developing new types of tools, increasing the sensitivity of detectors. And now we are living in the age of richness in the data. All the pursuit has been to try to understand how different structures lead to vastly different properties, and how can we design something that's going to have desired properties. But in this day and age of richness in data, we are actually often limited by data-driven challenges. So just to illustrate, I want to give you a relevant example. So X-ray diffraction in 1913, published in this Nobel Prize winning paper of Bragg and Bragg, looked like this. So rotate the sample by hand, and you measure the intensity, and there's a single shot, and you get this kind of curve. And from this moment in 1900s, the pressing question was, how do we go from this data to the actual structure of atoms in the system? And the groundbreaking progress came from what we now learn in introductory physics, the Bragg condition. Bragg condition was the very first example of a very successful forward modeling. Bragg and Bragg imagined that atoms might be arranged like this, and they figured that if the atoms are arranged with this spacing, it will lead to the condition for explaining a curve like this. This was a very successful forward modeling, and the fact is, 100 years later, we still do forward modeling. Now, the problem is the data volume is much bigger. We have much more information to deal with, and trying to fit all the details of the measurement is becoming more and more impossible. So to talk about the content of the volume of the data, see if I can. No, I lost it. Oh, I lost my mouse. Let me see if I can get back to it. So this video is showing how the measurements are done these days, and the arcs that are being crossed is showing the number of Brillouin zones each shot can cross. Modern facilities at various labs around the world collect terabytes of data in matters of hours. Now, to analyze that data set can take months and months, and even after months of effort, we would often not have seen the entirety of the data set. So what can we do when we face data-driven challenges like this? My group has been, for over the course of the last couple of years, have been pursuing different strategies for different types of data-driven problems, such as image-like data or spectroscopic data or high-dimensional data, four-dimensional data of STEM, or quantum system data, or even simulated data. And I want to talk about two specific examples, but before I go into the detail, I want to talk about the strategy. So the strategy generally is that we want to bridge between experimental data and theoretical understanding as data volume gets bigger and data structure becomes more and more complex, so that we can gain understanding following this track, or use the understanding as an input for designing experiment. And ideally, we would like that design decisions to be accessible, in the real time while the experiment is happening. So how do we make use of data science tools to bridge between data and understanding? As I talk about machine learning, I often want to emphasize that machine learning tools, data science tools, are really tools. So here's an example of a very powerful tool. It's an industrial grade blender. It's morning time here, and soon I'll be having breakfast with my family. For making smoothies, which we often have for breakfast, this is a really good idea. However, if your goal is not to make smoothie, if smoothie is not your problem, but if you want to make a guacamole and you want to enjoy, savor each of the ingredients and how they come together, you would rather use this Stone Age tool compared to this, highly modern, high-tech tool. In the same way, for scientific progress, especially in physics, which is a domain with long history and a very rigorous way, established rigorous way of thinking, any machine learning contribution to make actual progress, it's essential that we can interpret, that we know what's going on in what we're doing. And in order to achieve interpretability, it's important to try to stick to minimalistic tools that you minimally need for the particular goal that you have, the problem you have. So that's the strategy in my group. And let me move on to the XTech, which is the unsupervised machine learning approach for high volume X-ray data. This work was really led by Jordan Bentley, my former student. He made the really leading contribution almost single-handedly. We had a great fun collaborating with colleagues at computer science, and we were able to really bring different topics together. And key insights for how to look at data, of course, came from X-ray experts, Jacob Ruff, my local colleague at CHESS, and my collaborators at Argonne National Lab. So what does the data look like? Until I try to visualize this intensity, 3D intensity distribution of X-ray data, I thought I know how to visualize 3D. It's not 11-dimensional. It's not, 4-dimensional, 3-dimensional. I thought I know how to visualize. But if you look at this intensity distribution of what this is, 200, 200, 200, so 8,000 Brillouin zones, we actually typically worked with tens of or 100,000 Brillouin zones. So, looking at this and trying to find important wave vector that's going to lead to, that's responsible for some ordering is really near impossible. And it's almost not as daunting, but, my approach to this problem was similar to what I feel when I look at this big box bin of Lego sets. I have way too many Lego pieces, and I am way too often looking for the special piece my kids are asking. And if you try to do this, you quickly learn looking at one piece at a time is really not a good idea. And that's what a manual approach is. So what do you do if you don't want to look at one piece at a time when you can quickly lose focus? The first strategy that you will find is let's try to sort. You can sort by color or you can sort by shape. And once you have sorted, you can focus your attention to just that small set. And that's the kind of approach essentially that we've taken, except that for the X-ray data, we don't have obvious criteria like color or shape. So then what should we use as a criteria for sorting? How will we sort to discover something non-trivial and interesting? And the insight really came from the we wanted this tool to be very broadly accessible, useful, and we wanted to stick to really fundamental, simple principles for the wide applicability. And what we realize is that if we are thinking about ordering phenomena, what we are thinking in the back of our heads is that how microscopic interactions that gives Hamiltonian, which will lead to energy, is competing with the entropy, pressure from the entropy. And what's balancing the two is the temperature. So what we can use is how the data is evolving as a function of temperature, sort of as a criteria. So what we decided to do was to look at the intensity, which is free amplitude of density, intensity as a function of reciprocal space point, and each reciprocal space point becomes, say, a population, individuals that we try to keep track of. And their temperature dependence, the evolution is what we're going to focus. And we expect different clusters of temperature series. So for each individual Q point, tracking as a function of temperature gives me a series, that's the temperature series. And we expect different clusters of temperature series among populations of Qs, depending on the behavior, their nature underneath. And the approach that we've used is sort of similar to what you would use if you're trying to verify a speaker. When multiple people are talking, at the same time, if you record the audio signal of all of those, you would have this, big mess of a signal. But if you have a mechanism to sort the speaker, one mechanism that's been used as a very simple mechanism is a Gaussian mixture model. And when you use a sorting mechanism, you can sort into, in this case, 2 different speakers. So that's what we're going to do with the X-ray data. This is a single slice of data set from titanium diselenide, which we used as a guinea pig. It's a material that's well known for its charge density wave transitions. So when you start, you have this is a slice of 3-dimensional distribution. You have data set like this, and trying to keep track of all the Q points, including all these points in between where the action is happening, is not very meaningful. X-ray data set has this very sparse nature. So in order to make the algorithm run efficiently, we first do a pre-processing that's using sort of a data science principle to threshold this data set, which we don't just put a absolute floor, which can really mess up with the data set with a huge dynamic range. Bragg peaks have 100,000 times higher intensity compared to some diffuse peaks. And we don't want to miss the diffuse signal because that could reflect the fluctuations. That's very important to understand. So we have developed a pre-processing scheme, which you can see the details in our preprint. And this pre-processing takes the raw data. Now compare this to the voice signal. This is obviously much messier. This is plot of entire data set for each of the Q points that we are tracking as a function of temperature, and it's a huge mess. After thresholding and rescaling, we have something that looks a little more manageable, but this is still quite a mess. And this is what we are now going to feed into our sorting algorithm. The sorting algorithm, the clustering algorithm we used is Gaussian mixture model. So Gaussian mixture model takes this pre-processed temperature series now for just the Q points that we've decided to track. This is now d to the t-dimensional vector. That's the number of temperature points, the measurement, how many temperatures that it's been measured. And for Gaussian mixture model, you conjecture K, this is a number of cluster, distinct multivariate normal distribution. So this is a normal distribution, just a Gaussian distribution, which is multidimensional because of the length of my vector. That's the mean and that's the variance. And it's multivariate because we are assuming superposition of, we're assuming distribution among different normal distribution to model the entire distribution. So the hyperparameters to be learned are these weights and the mean and variance. And these hyperparameters are learned by using expectation maximization algorithm that searches for the saddle point of the lower bound of the log likelihood. And this is sort of like mean field theory. So once you've learned these hyperparameters, you can assign the cluster assignment for each of that individual reciprocal space point by using this weight that's evaluated using this mixing weight, pi. So it's as far as like machine learning algorithm goes, this is a pretty simple algorithm, and that's why we were able to tackle terabytes of data with this in 10 minutes, order of 10 minutes kind of time scale. So the particular scientific problem that I want to discuss that we've tackled with this approach is looking for the order parameter of phase 2 intermediate phase in pyrachlor cadmium rhenium oxide. So this is a structure, and you can see that unit cell is very big. This is a material that became first known as the very first known pyrachlor superconductor. That got the community excited, and as people started to investigate the material, it's been noted that there are at least three different structural phases. So at 200 Kelvin, there's a clear singularity in specific heat, which marks that this is a second order transition. And at about 113 Kelvin, there is a little blip, which marks potential first order transition. Despite this very sharp, clear thermodynamic signal, what is the actual order parameter going from this high temperature cubic phase to the lower temperature phases? And what kind of distortions are happening inside the phase 2 has been largely unknown, and rather actually there has been a lot of confusion. The confusion has to do with the fact that A, the structure is very big. There are a lot of degrees of freedom in here. And B, the distortions are very small. Despite the huge signal and the specific heat, the distortion going from here to here was very small, and it's been hard to detect. A specific puzzle is what was really brought to frontier by this paper by David Shee's group, where what is the primary order parameter going from here to there? There is symmetry lowering, there must be an order parameter, and what's the primary order parameter? And the two candidates that's been discussed are two-dimensional EU order parameter, EU structure for the order parameter here, versus one-dimensional T2U. So we went into this problem really wanting to nail the problem for once and all. And for that, we wanted to look at the data set in a very comprehensive manner. We analyzed about 8 terabytes of data. And when we put all of that into our clustering algorithm, looking for 2 clusters, something that's going to change at the 200 Kelvin. We don't tell the algorithm that something's going to change at 200 Kelvin. We just, the only parameter that we set going in is the number of clusters. So we said, okay, we are looking for 2 clusters, and the rest is up to the algorithm to figure out. And what's shown here is the mean and variance. I said, because we have normal distributions in mind, the means and variances are what we are going to learn. So this is the mean, and that vector, t-dimensional vector, is each of the points we've interpolated over the temperature span. So the 2 clusters were learned, and they differed by how their mean behaved as a function of temperature. So this purple cluster has this very order parameter looking, taking on behavior, and the yellow cluster showed much subtler change. Now this is a transition that does not lead to change in unit cell size, which means there is no new peak showing up because of higher periodicity. You do not get superlattice peaks. However, when there is a symmetry change, new Bragg position can become allowed by symmetry. And that's what was learned here. And this interpretation is immediate because all we have to do is to look at where the clusters are located in the reciprocal space. So this is a slice of reciprocal space to illustrate where these clusters came from. And we can clearly see that the purple cluster came from positions like this, which involve multiples of 4 and multiples of 4 plus minus 2. These are the positions that are now become available at the lower symmetry state, which shows that this lower symmetry state, this phase 2, has tetragonal symmetry. But by looking at the selection rule of these points, we were able to confirm that this is most likely EU order parameter. Everything that we could, every single peak that we could find was consistent with the ordering being EU order parameter. But I mentioned the EU order parameter is 2-dimensional. So now if you have a 2-dimensional order parameter versus 1-dimensional, the difference is like Ising versus XY. XY is 2-dimensional. And if you have a 2-dimensional order parameter, it means when you're lowering the symmetry, you're breaking continuous symmetry, which leads to Goldstone mode. So with a continuous transition, typically there is a fluctuation region. The critical fluctuation can be detected by X-ray. But if this is a 2-dimensional order parameter, there should be a Goldstone mode that is present in entire region of the lower temperature phase, this phase 2. Now, I make it sound like this was obvious, something that we were after in a quest, but actually the actual way in which this came about was from clustering result. We tried to see whether we can learn more about some fluctuating order parameter, something diffuse. So instead of lumping each Bragg peak region to be forcing them to be one cluster, we individually looked at every single reciprocal space points that passed our thresholding. And what we found was that the entire data set we can cluster with 4 clusters. And there is a cluster, this blue cluster, that shows enhanced activity. This up here is the transition into this phase 2, which we've cut down because we didn't want to be influenced by the critical fluctuation. This cluster shows enhanced activity over the entire phase 2. And then there's this other cluster that shows much lower activity in the phase 2, and then it shows a jump in activity, so around where the lower temperature first order transition is. And then there is a cluster that's showing relatively weak temperature dependence at this lower temperatures, well below upper transition temperature. Now we try to interpret what this is about. So we look at where they're coming from in the reciprocal space. Now I'm trying to show several Brillouin zones, but because the peaks are very sharp, the distribution of data is very tight. So let me blow up this for you. So this is a peak which has blue cluster in the diffuse region, and the center is a black cluster. And this is another peak which has red cluster in the diffuse region, and the center is a black cluster. So what this shows is that well below the upper transition temperature, all the Bragg peaks that are now well and alive have relatively weak, the center of the peaks themselves have relatively weak temperature dependence. However, the region around it, the diffuse region, for some peaks show this enhanced activity, and for some other peaks show much less activity. Now we went to the raw data to confirm whether what is actually going on, and we can really see, looking at a cut. This is a cut of this peak, cut along this direction. That the temperature is kind of blocked. This is a temperature range of the intermediate phase, phase 2. What you see is that there is a diffuse intensity over that entire phase or in the blue diffuse region, but in the red diffuse region, there is much less of a diffuse intensity. And this we were able to confirm is actually the signature of the Goldstone mode. This is the fluctuation associated with the Goldstone mode. Because it is associated with Goldstone mode, it is present all over the phase. And moreover, by looking at which peaks support these Goldstone modes and which do not, we were able to infer that this Goldstone mode fluctuation has primarily to do with the antiphase movement of rhenium and cadmium. So going back to, so this is the crystal structure. So there are rheniums and cadmiums. Rheniums are in the center of this tetrahedra. And they are having this antiphase C-axis motion, which is the distortion and the fluctuation that's responsible for this phase. So now, having confirmed that there is a Goldstone mode, I think we really nailed that the nature of the order parameter here is two-dimensional EU order parameter. Now, that's for the X-ray diffraction data, or which we believe is applicable to other type of reciprocal space data. And maybe it's not the temperature, but some other control parameter that is balancing between the Hamiltonian of the system and the control that you're applying. Now I want to turn to more recent work, which we don't yet have a preprint, but I'm really excited about what we were able to do. So I want to talk briefly about it. This is looking at the real space data quantum gas microscopy data. And what we are calling it is correlation CNN. So this work was again in collaboration with my colleagues at computer science. It was spearheaded by my first year graduate student, Cole. He's just really blew me away. In less than a year, he almost has a paper with very exciting results. And this is in collaboration with colleagues at Harvard. So quantum gas microscopy is it's a powerful way to explore ultra-cold atoms that's simulating quantum matter. It's a very new type of measurement, but that's widely adopted by ultra-cold gas community. And the most exciting result the community had has been that they can simulate the Hubbard model and now go down to low enough temperature to see magnetic ordering, and then try to move up in doping to see pseudo gap and strange metal kind of physics. Now the problem is when you look at the data and you want to interpret, you want to infer which theory is describing these mysterious phases, like pseudo gap phase, which does not have an obvious order parameter. It does not tell us what pattern to look for. And you cannot, open up Ashcroft and Mermin and figure out how should we analyze quantum gas microscopy data. The two theory ideas that we wanted to tell apart specifically for the pseudo gap phase was the idea of geometric string, that when you dope hole into antiferromagnet, as the hole moves like this, it leaves a wake of wrongly aligned spins behind. And the other was the pi flux theory, which is starting from the singlet bonds, RVB, resonating valence bond state, and trying to think about what the added holes. This is all about trying to dope holes into this, the Hubbard model, and what kind of states one would get. And there have been already efforts to use off-the-shelf CNN, convolutional neural network, TensorFlow. A lot of these architectures are now easily available. A problem is for such a small data set with small number of degrees of freedom, off-the-shelf CNN involves over-parameterization, way too many parameters, and it's a black box. And what we are proposing is to use a simpler architecture, which involves correlation functions. So the idea is you start with the data, and you would have your convolutional layer, which involves filters. But then you look at higher powers of the convolutional layer that you can construct. From combining all of those, you try to learn what's going on in the system. And the idea is this will allow us to actually interpret, not just say, okay, these filters fired. Even if when you know which filters fired, because of all the nonlinearity that's very complex in convolutional neural network, you don't know what to make of the filters. However, in correlation CNN, CCNN, these cascade of filters cascade of convolutional layers all goes back to a single convolutional layer with single set of filters. But we use this controlled nonlinearity so that we can figure out what is going on. Once we have a trained CCNN, the way we can figure out what is important is using regularization path analysis. So for regularization path analysis, we are looking at which of these layers of higher order convolutions made a meaningful difference in accuracy. As we turn them on, we allow them to turn on. Which one turns on first, giving higher accuracy? This is kind of a lasso approach. And this is these are examples of two filters that were learned. Our filters were 3 by 3. That's why you're seeing 3 by 3 pixels. There are 3 channels: spin up, spin down, and hold. So now what do we do once we've learned which filters are important? At what order? Now here we see that fourth orders mattered. Okay, so that's this C to the fourth power. So when a fourth order matters, what it means is we can trace it back to fourth order being important to be a 4-pixel pattern. It's a fourth order correlation. So now we not only know the filters, we know what order, what level of non-locality that they mattered. Because it's fourth order, we are going to now look for 2x2 or an other 4-pixel pattern. And you can do it visually. So here is one channel, red channel with 2x2. If this gets combined with, let's see, okay, let me choose this one. Okay, these 4-pixel, and these 4-pixel, and these 4-pixel together can give you either this pattern or this pattern with red, blue flip, or these are the patterns that you will get. So now that we know the patterns, we've learned that these were the motifs the CCNN learned to be important in trying to tell apart the geometric string versus pi flux. And we can now try to see whether that makes sense. Did we learn something meaningful, or did the CCNN learn something meaningful? Now you can go back to what the geometric string theory says. Geometric string says, I'm going to move my hole, it's leaving behind this wake. And if you look at the whole motifs around that wake, you see the patterns that are learned here. This is a pattern that was learned. This is a motif that was learned that has to do with the single hole. This is another one. And this way we were able to figure out, okay, if we want to tell apart geometric string from pi flux, it's the fourth order correlation that matters. And typically, if you open up any textbook, you'll see the order parameter itself. Maybe you'll see the second order correlation. Nobody talks about fourth order correlation. But turns out for this kind of extended objects, this is what mattered. This is an example of what we were able to learn with CCNN, and we believe this approach can be broadly applicable for other image type data, which we are increasingly becoming richer with image type data. So on that note, my time is up. Let me just summarize that I talked about 2 specific examples, but generally, if we take the approach of trying to identify what is the data problem that I have to solve, and what would be the approach that can attack that data problem most efficiently, we can really make use of the richness in data that's available and make scientific progress and leaps. Thank you for your attention.
Thank you very much, Una, for this super nice talk. So again, I invite everyone, if you have a questions, just type them in the chat and I will read them out. While people are preparing their questions, let me start with just a small technical thing. So with this correlation CNN, so it's not supervised training. You fix the filters first and then it's unsupervised, or you have some kind of labeled.
Good question. So so it is a supervised training. So supervised training is the part that I didn't emphasize too much. So supervised training is what leads to fixing of the filters. So we do supervised training with the label data set, but the part that I went in detail was about how you interpret the trained neural network. So supervised training leads the network with some fixed hyperparameters and the filters, for instance. And each training run will lead to get us to different filters. The point is figuring out what matters is really difficult, even if you know what filters were important. And CCNN is designed to allow us to interpret from the beginning. So its architecture allows us to learn meaningful things out of the filters. I don't know whether that answers your question.
Yeah, definitely. I understand now. I just kind of, I needed to understand about the training.
Yeah.
So maybe then like a bigger picture question, you were talking about like, so it seems like this unsupervised approaches are are super powerful, but then maybe they are harder to verify. And then this like tailored supervised architecture, they can be really good at picking up some particular features. So if I would ask you what's like a your general vision for this field of like a big experimental data processing, would you like more bet on the unsupervised, or what you are doing now that is a combination of both? Like where would you say you see this field going now?
That's a tough question. Both comes with difficulties, but perhaps as I try to see how what we do with machine learning can meaningfully contribute to science, supervised learning often has the issue of facing the bias, because your training set has built the bias in it. So I still do supervised learning because you can learn a lot of things that way, but I try to so if I do supervised learning, I want to be able to interpret so that I know what it's making the decisions on. For instance, using CCNN, we were able to figure out when we give the experimental data compared to the simulated training data, CCNN learns subtle difference that's not a meaningful difference, which we didn't think was important as a key feature in the experimental data. So I've done this many times, and other people do this too. People use simulated data to train neural network and then give experimental data, because we have large data sets or complex data sets, but we don't have 10,000 copies of them. Now, the problem is neural networks don't generalize well, and you don't always know what did it learn. So I think supervised learning is fine. And I've been more often than not really pleasantly surprised that, gosh, it learned the right thing. Good job. But it's really important, especially if you're mixing simulation and experiment, it's really important that we know what it's learning. So I think having interpretation in mind from the beginning, rather than just taking something and hope that maybe I can make something out of it, thinking from the beginning as a physicist, own the problem and think about, how will I interpret when I'm done? I think that's really important, especially with supervised learning. Unsupervised learning approaches are either sort of probabilistic thinking like we've done, or some dimensional reduction clustering approaches. And those are also in their own right, often they can be hard to interpret. So, even for those, I think being able to interpret is important. When talking to people, our colleagues out who's not initiated with machine learning, unsupervised learning can be more compelling because you can say it was unbiased. And for X-Tech, what we've done is really pretty simple, but it was we were able to sort with criteria that makes sense to us. If you just do k-means clustering, you don't necessarily know what is the criteria that is being used in this high dimensional space. You don't know the spread. So I believe in trying to use simple tools and trying to keep physicists thinking from the beginning involved, rather than just trying to take somebody's tool and hope it will work for you.
Thank you so much for this perspective. So let me finish. We have one question from Evert van Nieuwenburg in the chat. Do you have any insight into the dependence on the size of the convolutional filters? What I mean is the following. Would you get away with second order correlation if you had 6x6 filters, so that you can capture the 2x2 correction of the 3x3 and so on?
So what we've learned, which I'm not sure whether I've given a, right. So these are the way in which we build up the convolution. And you can see from here, this is nth power in the image. So linear order, the first order is no matter how large the filter is, it's just the sum. It ends up just being the sum with some linear sum. Nth order is correlating more and more pixels. So no matter how large the filter is, as long as the filter is larger than 2 by 2, we've learned the fourth order correlation to be most important. That seemed to be minimally what the neural network needed. So we did try 4 by 4. We haven't tried 6 by 6, but we did try larger filters, but it didn't seem to make a difference in terms of this fourth order correlation being the issue. Before we actually tried this, those of us who were involved didn't really realize that the order of filters mean really the number of pixels that we think together. So fourth order meant that we are going to think about 4 pixels together. So in this case, like this is another 4 pixel. It's not 2 by 2 block. These were all the other 4 pixel patterns. I hope that answered the question.
Yep, thanks. That makes sense.
Thank you.
Okay, perfect. We are running a little bit over time, so let us finish here. I would ask everyone to turn on their video now, so the organization can take a final picture of the whole session. While they are doing that, I would like to use this opportunity to advertise our afternoon discussion session. I am sharing in the chat the link for we had some pre-recorded talks and 1-minute poster pitches. So in the YouTube channel, you can go watch the pre-recorded talks and poster pitches. And in the afternoon, we will do like a discussion and a breakout room where you can talk to the person of the poster or the pre-recorded talk that was interesting to you. That starts at 5 p.m. European time, so approximately 4.5 hours from now. With that, I hope that the organization had time to take a picture of everyone. Big thanks again to all of the speakers of this session. I think this was really great, and thank you everyone for attending and listening, and I will catch you later in the afternoon sessions.